Talk today is Nathan Urban. I have a bio here, but I'm not going to read it all out, but just opening sentence: Energy Security Fellow in the Computational Physics and Methods Group at Los Alamos. We've already seen a picture of Los Alamos. It should be remembered it's 7,000 feet. There's a long drive from Albuquerque to get there, and so do try and go there. You can always stop off at Santa Fe and pretend you're a hippie. Okay, Nathan. The title is up there, so it's too late in the afternoon to read it out.
Right.
Thank you very much.
So I work a lot in the area of climate uncertainty quantification. And the thing to understand about climate modeling is that there are a bunch of different climate models out there. There are 20, 30, 40 or more. It kind of depends on how you count different versions of different models. Are they a separate model or part of the same family? But we have a couple of dozen of these things. And they have quite a few differences in what they actually predict into the future. So if you look at the graph here, you see envelopes of temperature forecasts from different climate models. Each color represents a different emission scenario, so a different rate at which human beings can combust fossil fuels. And the width of these bands represents the spread across different models within one of these emission scenarios. So if you look at the high emission scenario, that's the red one, you can see that if you were to go out, hundreds of years, you have like this enormous uncertainty, which is why no one bothers to do that. But also because decision makers kind of focus on the nearer term uncertainties. But even if you go out to things within the century, up to the year 2100, you can get an uncertainty range of over a degree, degree and a half, just by changing which model you're looking at. And that spread is on the order of magnitude of the differences between scenarios. So if you look at the difference between the blue and the red, the width between those two scenarios is similar to the uncertainty band within one scenario. So it's a first order uncertainty in the problem. Why do they have these uncertainties? They're largely due to differences in how the models simulate climate feedback effects, which dynamically amplify uncertainties over time. So a small uncertainty, once you subject it to an amplifying feedback, can become a large uncertainty later. So for example, the climate sensitivity is a quantity that we talk a lot about in climate science. It's defined as the eventual global warming that we'll experience from a doubling of atmospheric carbon dioxide concentrations due to the greenhouse effect of that carbon dioxide and the feedbacks. So here's some examples of feedbacks. One is in a warming world, there's more evaporation of water off of the oceans. That water vapor goes into the atmosphere, but water vapor, like carbon dioxide, is also a greenhouse gas, and that causes additional warming besides what the original CO2 did. Another feedback is you warm the planet, you melt ice, you replace the ice, which is highly reflective, with something underneath it that is not so reflective, like soil or ocean, depending if it's land or sea ice. That's darker, it absorbs more sunlight and causes more warming effects. If you look at probability distributions for this climate sensitivity, you have that over on the left, and you have a whole bunch of distributions depending on who's doing the estimating, but they all kind of have this feature that they kind of peak around maybe 2 degrees Celsius warming for doubling of CO2. By contrast, that would be about 1 degree of warming if you didn't have any feedbacks, if you just had the greenhouse effect of the CO2. But they have this long tail, and they can run up to 3, 4, 5 degrees, occasionally even higher. And the feedbacks are highly correlated with the warming that you get. In this scatter plot, this is a plot over a perturbed parameter ensemble of a climate model. is the colored dots, and also the black dots are the multimodel ensemble, where we have all these different modeling centers throwing their models in. And you look at the correlation between the cloud feedback, so clouds can change their reflectivity or amount or other properties in a warming world, and the warming that the model experiences. There's a strong linear relationship. So these are strong controls on the spread of warming that you get out of a climate model, can be traced back to uncertainties in the feedbacks. Which leads us to multimodal or structural uncertainty. So why do these models differ from each other? They differ in ways besides just parameter uncertainty. They differ in the approximations they're making numerically. There are parameterizations, which are approximations for processes that can't be resolved. Like if you have a 100-kilometer grid cell, you can't really resolve a cloud, which is sub-kilometer scale sometimes. So you have to have a bunch of approximations for what average cloud behavior is doing within that grid cell. There are processes that are included. Some people include more processes, some include less. And so depending on what choices you make and what you put into your model, you get a different model. And this leads to multimodal uncertainty. The more general concept would be called structural uncertainty. It's kind of fuzzy because sometimes you change something about the structure of a model and you don't say you have a different model. You have a new version of the same model, but that's completely fuzzy. So I kind of use these terms interchangeably a bit. So a standard approach to multimodal structural uncertainty quantification is to just average the models together. You compute the mean of all the model predictions, you compute the variance of all the model predictions, and you are done. That is uncertainty quantification. That's still pretty commonly used. Sometimes if you want to be fancy, you try to weight the models. You say, well, this model is better because it agrees with the past history better, and so I trust it more. I give it a higher weight. But this approach has limitations. One is that you shouldn't give a model a single weight because models are good at different things. This model might be better at representing cloud feedbacks because it has a really good atmosphere. Another model might be really good at representing the response time of the oceans as they take up heat over decades because it has a really good ocean. Another issue is that the historical skill of a model isn't necessarily correlated with what it does in the future. So if you try to use that as a skill weight, you're in trouble. Sometimes this is due to over-tuning. So all the models kind of get the historical 20th century warming rates correct. They all basically do the same thing, so any differences between the models in that regard could be pinned down to essentially noise. Now, of course, you can go to more specific metrics than global average temperature, and then you'll start seeing more differences that really do reflect model fidelity. But another issue is that the things that make a model good in the past may change in the future. So maybe a model was really good in the past because it was good at reproducing the Pacific oscillation and patterns of multi-decadal variability that we observed. But in the future, if the spread in models is completely dominated by, say, the cloud feedbacks in those models, then it doesn't really matter how well it got the historical global temperature. It might have gotten it for a different reason. What you really care about is it getting those feedbacks correct. That's what you'll trust into the far future. Yet another problem with averaging is it doesn't give you anything not in the set of models that you're averaging. You just weight them together, but it doesn't give you an n+1 model. It doesn't sample into the tails of the distribution if you care about risk and you're a planner. And it might not even make sense. So if you have one model that has El Nino that comes by every 2 years and another model that has an El Nino that comes by every 6 years, and you average those together, you get some combination of a 2-year El Nino and a 6-year El Nino. You don't get a 4-year El Nino, even though that might be a realistic possibility. So here's a long list of problems. How do we approach this, a solution to these problems? Well, what we'd ideally like to do is somehow sample the space of possible model structures, the way that we sample parameters, sample different models, But this isn't really possible. You can't subsample every possible model that anybody could ever conceive of constructing. But nevertheless, let's try to think about how to approach that ideal and what are different ways that you could try to get your head around that sort of problem. What is the space of all possible models anyway? So the main idea, and I'm going to talk about 3 ideas that attempt to tackle this problem. But the main idea that they all share is that we're trying to convert structural uncertainty back into parameter uncertainty, which we know how to deal with through Bayesian parameter estimation. So what we're looking for are what are the relevant effective degrees of freedom that represent a model's structure? How can we encode the differences in a model's behavior in some low-dimensional parametric way? So one idea for those degrees of freedom is that you try to parameterize the things that are causing the multimodal uncertainty into the future, like differences in feedbacks or differences in response timescales, e-folding times or whatever. And you can try doing that using a mechanistic reduced model that has those degrees of freedom built in by design. Or you could do something a little bit more semi-empirical or statistical dynamical, where you're trying to describe the modes of variability and couplings between them in some sort of empirical way and allow those to parameterize differences in what the models do. The second idea I'm going to talk about is, well, let's try to use the governing equations themselves, the actual equations that the model is solving, and try to somehow parameterize and explore differences in those equations. And then finally, the last idea is to look at statistical relationships between observables, inputs and outputs of the system. An input could be carbon dioxide and an output could be temperature, and let's try to just parameterize that relationship directly rather than trying to dig deeply into the dynamics. Anyway, regardless of how you do it, once we have defined these structural parameters and start perturbing them, we're going to look at using reduced or statistical models to predict what are the effects of these perturbations in the model structure upon the predictions of the model. So here's the first idea. Using reduced models as emulators of the multimodal ensemble. So here is a little differential equation. It's just got 2 equations for surface temperature of the planet, average over the whole globe. It's just a number, average temperature. It's a function of time. And then it's also got a temperature of the upper ocean. So it's what we call a 2-layer energy balance model. It has heat where it warms up the atmosphere and maybe the mixed layer of the ocean, and then it's got some deeper layer of the ocean, and they transfer heat between each other. So you have a reservoir with some heat capacity, and they're coupled together. You don't need to know all the details of this, but basically you have a forcing term, which is the greenhouse gases. They have a radiative imbalance. Then you have a feedback term, the minus lambda T, that has some sort of amplifying or suppressing effect on the warming depending on what lambda is. So that controls how much warming you get relative to your current climate state. And then there's a heat transfer term between the surface and the deep ocean. And so in the figure here you have some idealized computer model experiments where we instantaneously quadrupled the carbon dioxide in the atmosphere, and then we allowed the temperature to gradually respond to it and approach some new equilibrium temperature. And we did this is done for 3 different climate models. This is just downloaded out of the Multimodel archive. Everybody submits these things when they build their models. And the black curves are 3 different climate models. And then the magenta curves are fits of this little energy balance differential equation to the 3 different models. So you can see that if you only care about this aggregate observable global average temperature, this reduced model does a really good job at fitting what the extremely complex numerical simulations with all this fluid dynamics and clouds and everything else are doing, because we've captured what are the important degrees of freedom. They are the feedback factor lambda, and they're the heat transfer coefficient gamma, which controls the response timescale. How quickly does the planet warm? 10 years, 30 years? It's an e-folding time, basically. And so, just continuing on in this simple example, what we've done is we've fit the same reduced model to 3 different complex models by tuning its parameters differently. So consider this idea where you have some parameter in this reduced model. I call it a meta model here, but it's all the same thing. Say it's lambda, the feedback factor. Suppose you have 5 different climate models and you fit the energy balance model or the reduced model or whatever you want to call it to those 5 different climate models. You're going to get 5 different estimates for that parameter in the reduced model. You can then imagine combining those 5 estimates into some smooth distribution, treating them as samples from something that we want to estimate. That's the red curve. And we're going to do this through a hierarchical Bayesian model to combine the estimates from the individual models. But what this gives us is what we call a model-based or a physics-based prior for what we believe about the structure of these climate models, where the structure is now parameterized in terms of their feedback and response time scale. So this is what the numerical models say about feedbacks and time scales. But we can take it a step further and say, well, okay, well maybe those models are biased. Maybe their feedback factor is wrong compared to what has been historically observed. So we can then also introduce a database estimate of the feedbacks purely from the observational temperature record that's been measured, and that would give us something like the black curve. And you can combine the two using a Bayesian update, sequential Bayes update, to take your prior, add a new data source, which is the historical data. The prior is based purely on models, and get a posterior that represents a blending of the models and the data, or kind of a dynamical bias correction where you're fixing up their feedbacks in a way if they're biased. And of course, you could also just do this purely observationally, like why do we even need climate models? But the problem with trying to estimate these things purely from the observational data record is that it's short. And so you're going to get a lot of uncertainty, and you're going to get a long tail, and you're not going to be able to rule out some of these high climate sensitivities. But if you look at the models, and if you trust the models, you might say, well, I have a greater belief that climate sensitivity is centered around what the models say it is. It's not exactly what they say it is, but that's my prior. And then I can use data to update that. So I'm not going to dwell too long on the math, but what you write down is basically if you have the time series of temperature from an individual model M, that's a temperature time series, then you say that that is equal to the energy balance model's predictions for some parameter settings, theta of the energy balance model, plus some discrepancy noise process, which is an autoregressive process, and you can estimate the parameters of that too. It represents the spectrum of natural variability within the model. And then for each of these models, you can estimate the energy balance model or reduced model parameters, and you get a collection of PDFs, one for each climate model. You get a PDF of parameters in the reduced model corresponding to that numerical climate model. Then comes the model combination part. You assume that the parameters corresponding to each one of these Earth system models or climate models are drawn from some underlying multimodal distribution, which let's just say it's normal to start off with. So you say that the models are all scattered normally around some multimodal mean in terms of what their climate sensitivity and other parameters are, or feedback factors. And then you do a joint Bayesian inference for the parameters fit to each individual model, but also these underlying multimodal climate sensitivity and other reduced parameters. So this is probably easier to understand visually. I'll just focus on the climate sensitivity, which is not a parameter in the energy balance model, but it can be derived from the feedback factor and the heat capacity and the other parameters. So if you look on the left, you get probability distributions which result from fitting the reduced model to each complex model, and you get, like 19 different probability distributions. And then when you apply the hierarchical model combination idea, you get over on the right the green curve. And this represents kind of the model blended uncertainty. Now by comparison, you could say, well, what if I just took those 19 probability distributions and equally mixed across them, an equally weighted mixture distribution of those 19 things? Then you get that light gray curve, which has all these weird multi-modes and bizarre structure to it. We don't actually believe that the real distribution of multimodal uncertainty has all those weird peaks and other odd structure in it. That's just an artifact of the fact that we only have 19 models. What we actually believe about multimodal uncertainty is that it's something smoothed or blended across all those model estimates, and that's something that the hierarchical model provides. Now, by comparison, we also did some approximations. So the blue curve is what you get if you do 19-point estimates. You just do a least squares best fit of the reduced model to the 19 numerical model outputs. And you get 19-point estimates, and you just compute their mean and variance and assume that that's normal. That's the blue curve. And then the red curve is where you take this mixture distribution and you do moment matching. Again, a normality assumption. You compute the mean and the variance of that and assume it's normal, and it's a normal approximation to the gray curve. So you can see that they're all kind of like each other, but they're not exactly the same. And so I guess a question for future research is, do we need to do the fancy hierarchical thing, or can we get away with one of these simpler approximations? The hierarchical assumption will allow you to import more kind of assumptions about how models are related to each other than just doing a normal approximation, but we haven't taken it that far yet. The other thing that the hierarchical model does is regularize estimates. So if I estimate climate sensitivity for model 13, once you make the hierarchical assumption, you're really saying that all the model's climate sensitivities are related to each other. They have a dependence. They're drawn from some common underlying distribution. So my estimate for model 13's climate sensitivity should actually be influenced by my estimates for all the other models' climate sensitivities, and it should draw my estimate for model 13 towards the multi-model mean. And that's actually what happens. Over here, for all the models are some spreads for the climate sensitivity that we estimate for each model. And then when we do the hierarchical thing, it pulls the spreads in, so it kind of cuts off some of those tails and pulls them all closer to each other. And we can debate how desirable that is. But the last thing we can do is the Bayesian inference with historical data, the update. So the green curve is our physics-based multi-model prior, and now we've put the actual observational record, which is the black curve, on top of it. And if you look at the green bands there, the gray lines are all the different models, just the raw model output, and the green bands is some 95% interval or whatever. But the models are running warm relative to the observations in the mean. Some of them pass through the observations, but some of them are passing above. And so if we do a calibration of the climate sensitivity, we take the climate sensitivity we get from the models, and then we apply the temperature constraint, and it says, oh, you need a lower climate sensitivity to fit the data. And that's these dark curves here, which I've done for various different versions of the temperature record, which are all slightly different. So it pulls the climate sensitivity estimate down, and then you can run that through your reduced model forward to a posterior predictive distribution, and then you get the magenta curve, which is a lowered, dynamically bias-corrected projection of what you would get from the multi-model ensemble if you tried to fix the average climate sensitivity and other dynamical properties of the models in that ensemble. So this is all within the univariate setting. Of course, we'd like to do this where we have spatial variability, the space-time variability in the climate. And so there's lots of different things that I've been looking at. I don't have enough results to really present, but we've looked at continuous time approaches. So we look at differential equations, but with 2D structure to them, so a 2D energy balance model that diffuses heat horizontally. Or we can take all the climate modes and project them onto principal components and then try to write down a stochastic differential equation that describes how those modes evolve. That turns out to be really annoying, and I've abandoned that. So I'm looking more at discrete time approaches where you do just traditional vector autoregressions, multi-level regressions. You can also do something interesting called dynamic mode decomposition, which is an empirical approach to reconstructing the dynamics of a model from just snapshots of its output. And I'm not going to go into a lot of detail there, but the idea is assume that you have some nonlinear operator that takes the state of the system, the multivariate state of the system, forward one time step, where one time step might be a year or however often you have snapshots. So you have the temperature field everywhere on the planet at this year, and then there's some nonlinear operator that will evolve it to the next year. The idea between dynamic mode decomposition is to take this nonlinear operator over a finite dimensional state space and lift it up to an infinite dimensional linear operator over a functional space. It's kind of reminiscent of the kernel trick in a way, but it's not exactly the same thing. And then you compute eigendecompositions of that linear operator and then truncate them and then map back onto your finite space when you want to use it for predictions. So I will say no more about that, but you can look it up if you're interested. Second idea is, well, let's go back to the governing equations. All of these models are solving PDEs, which is some discretized approximation to some continuum equations. So if models differ, they differ in either the underlying continuum equations or how they're being discretely approximated. So suppose we have, dx dt equals some n of x. If we were able to parameterize n itself, this nonlinear operator that is the system equations, we would be able to explore different model structures. But one problem is we don't know what that operator is. I mean, it's not just you have like Navier-Stokes and you discretize that using your favorite, finite whatever method and get an answer, because in a climate model you might have, some lines of code that implement the fluid dynamics, and then for every line of code that does that, you have 10 lines of code implementing all sorts of crazy approximations to all the stuff that you're not resolving, like clouds. You have empirical regressions stuck in there, fit to experimental data. You have if statements, fixing things up in the model. It's this, God knows what is in there. You can't assume that you know it. It's just like a million lines of code. I mean, you can't manipulate that mathematically. But suppose we can learn the governing equations somehow. Can we then automatically perturb them and make predictions about new model structures? So here we're looking at what I'm calling kind of quasi-intrusive reduced modeling based on Galerkin projection. So Galerkin projection is a well-known reduced modeling method that is intrusive. If you have the dynamics of the system, the n of x operator, and you can write it down analytically, and you have some basis of the output, the state vector, then you can project down onto the basis and come up with a new set of differential equations just for the reduced modes of the system. And then you just solve that smaller differential equation. There's details to make this efficient. You have to kind of emulate some steps of this, because to actually pull this off, you have to take the reduced vector, lift it up to the original space, apply the nonlinear operator, then project it back down. But if you're doing that lifting, you're not really reducing or saving anything. So there are methods out there that try to get around that through approximations. But I'm not going to get into that. The point is that I want to make this method non-intrusive. So here's the central idea. If you're solving a PDE, suppose you're just doing the simplest finite difference approximation. what you have is like a stencil operator. You have like, you're computing a Laplacian in 2D, so you've got your 5-point stencil where you're averaging over neighboring grid cells, and you apply that stencil operator everywhere in the domain that you've discretized. I'm calling this, in general, not a stencil, but a local dynamical operator, where the key fact is that it is local. It is the same operator being applied everywhere across the domain. So let's try to learn it from the model output. If I run the model and I evolve it forward one time step, then the value of the state at a given grid cell is just a function of its state at the last time step plus the state of its neighbors within some stencil region. So this is the locality assumption. And then once I learn that through some statistical regression or function approximation method by just looking at model output, then I want to perturb the operator. So, the red dots there, that's kind of like our numerical stencil. So the state at that central point depends on those 5 points. It's just a function of the state at the 5 points. And so if you treat it just as like a function of 1 point, you're going to get some weird looking function. That's the black curve. And that's basically the state at time t plus 1 as a function of the state of time t. And that's, depending on your dynamics, could be anything. But whatever it is, you can start perturbing whatever that function is, and that gives you new dynamics that are similar to the original dynamics that you started out with, which you can then project onto your basis. Those are some spatial basis functions to get perturbations of the reduced model, the Galerkin projected model. So here's an example. Two-dimensional rotating shallow water equations. I'm not going to get into them, but it's just kind of water in a plane that's rotating. You discretize that. It turns out that the dynamics become quadratic in the state variables. So we try to recover that quadratic operator through regression just by looking at a bunch of samples of running the model. And we can recover those operators. These x's are all the coefficients in this. I just put in every possible generic quadratic nonlinearity, but only some of them are non-zero in this system. And so we recover all of the x's pretty closely, plus a whole bunch of noise. There's a whole bunch of very small non-zero things that it wasn't able to rule out just by looking at the model output. And we don't have to assume that this is polynomial. We could do a Gaussian process instead of a quadratic regression or whatever. So to improve what we're doing, well, one thing is we do sparse regression. So we say, well, most of these are going to be 0. So then they actually become 0 and we recover things better. We also force this operator to respect physical constraints like energy conservation. We could try to reparameterize the operator analytically so that it always exactly preserves energy conservation, but that's probably not going to work in general in a more complicated system. So instead, we're basically imposing a regularization, a quadratic regularization on its deviations from energy conservation, and we're requiring all the operators that we consider to be very close to energy conserving, although not necessarily exactly. And you could, in principle, do that iteratively, so you kind of get them closer and closer to energy conserving through history matching type ideas. And finally, in our regression, we're building in some physical knowledge of the system. So here we're going to assume that our dynamics are unknown, but they depend on some operators, gradients, Laplacians, whatever, whose stencils are known, and it's some unknown function of those operators. And that will also help us out in recovering things. The final thing is, well, suppose, we've learned this all from a numerical model where we have everything we want. We can run it at the time step level, evolve it forward a millisecond in time or whatever, and get as detailed information at whatever resolution we want, computation allowing. But in the structural uncertainty problem, what we have is some observational data, and we want to explore different model structures that are consistent with the observational data. So what we do is we start with a dynamical operator that we estimated from a numerical model. We have one numerical model and we have an example of its dynamics. But we're going to assume that the real world might be somewhat different from that model in terms of its dynamics. And we can say, can we recover what those dynamics are just from the observational data, which might be much coarser or sparser or aggregated than what the model output itself provides. So we've done a perfect model experiment. We ran the simulator, and then we kind of averaged it. We blocked it over, you know, some coarse regions in space, and we said, okay, suppose that's what we observed. Can we recover what the operator was consistent with that data, and how many operators are consistent with that data? So going into this operator space, this quadratic regression thing, we just pulled out two of the key parameters that it's very sensitive to, and we said, how well could we recover the original parameter settings that the course and data was derived from? And you can see in most cases, you know, the posterior for those two parameters, the joint posterior lie, you know, completely encompasses the true value, so we're doing a good job at recovery, except for this case where we ran the model for a long time, and the reduced model, the Galerkin model, started diverging from reality due to truncation error in the finite basis of the model. So it misconverged to the wrong. We were more certain than we really should be. And in principle, what we need to do is include some discrepancy to absorb the possibility that the reduced model is not completely representing the dynamics of the system due to the basis truncation. So finally, here's my third idea, and very quickly. Here I'm looking at what I'm calling modular uncertainty quantification, which is looking at more of an information fusion type setting. So what we normally do in kind of computer model uncertainty quantification is emulate the output of a complex numerical model. We perturb its parameters, build our GP emulator. What I'm doing here instead is building a Bayesian network of emulators, where each emulator represents kind of a response function from the output of one model to the input of another model, or output of one process, rather, to the input of another process. And the setting here is, suppose we want to figure out like the uncertainty in coastal flooding. Well, it goes through this kind of causal chain of dynamics. First, the surface of the planet warms. Then the ocean warms. It changes the ocean circulation, the deep ocean circulation. That melts ice from below, floating ice shelves around Antarctica. Warm water comes under them, melts them. The ice retreats. You get sea level rise, which floods coasts. The ocean warming can also create more hurricanes, and that also floods coasts. So you've got this graphical model at the end of the day. And so what we tend to think in climate science is we're either doing perturbed parameter ensemble experiments with a single model, or we've got the multi-model ensemble. But in reality, we have more than that. We have not just these global climate models, but we have regional models. You might have a model that just applies to Antarctica. It's on a limited domain just around that continent. You might have an idealized model where it's just like an idealized ice shelf geometry that doesn't describe anything real. It's not the real shape of an ice shelf, but you can run it at extremely high resolution and therefore learn something about how the ice shelf responds. So in principle, you should be able to use that information, but how? So what we do is we decompose the system into these processes, and we assume that different models or different data sets might be informative about different parts of this graphical network. So you might have this idealized model that applies just to the ice retreat part. It's an additional piece of information that doesn't exist anywhere else in the system because it's just a model of ice retreat. And we want to somehow include that. So here's an example of what I'm calling a process emulator, which is an emulator of one link, say ocean warming to the circumpolar deep water. That's the ocean circulation around Antarctica. So what this really is some kind of a conditional response function. If you think of just a number, how much did the global ocean warm? And then if you look at, in a model, how much the ocean, the coastal ocean around the Antarctic margin where all the ice lives, how much did that warm? And you can look at the time series of global ocean warming versus the time series of coastal Antarctic warming and do a scatter plot of that within any given climate model. And that's the gray curves here. You get a bunch of scatter plots, one for each model. And you can treat those as linear relationships. These are linear fits, are the red lines. So you can see that some models have a very large amount of Antarctic coastal warming for a given amount of global ocean warming. They're more sensitive to the global ocean warming than other models where you might have a very mild response of Antarctica to the global ocean. And there are physical reasons why you might expect there to be differences, but the point is that you can take this sort of information and treat it as a response function. If I know the global ocean warming, what is the uncertainty in Antarctic coastal warming? And so here I've built another hierarchical Bayes model, except this is just a linear regression now instead of something with some nonlinear differential equation in the middle of it. Just a bunch of hierarchical or linear regressions pooled together hierarchically gives me some envelope of uncertainty. So if I pick 1.5 degrees of global ocean warming, I get some range or distribution of Antarctic coastal warming. And so this is what I'm calling a probabilistic process response function. And I want to build a network of these things trained to different data sets. Here's a toy example. Start with that energy balance model that I was using at the beginning of the talk. It gives global surface temperature warming over time. Then hook it up. It also gives ocean warming, by the way, because it has that ocean layer. Then hook it up to the response function I just showed you. That is a conditional relationship that says, given ocean warming, what does Antarctic coastal warming do? Then I hook it up to yet another thing, which is an impulse response simulator of an Antarctic land ice model. So people run these land ice models, and they impulsively just give them an instantaneous temperature perturbation underneath their ice shelves to start melting them. And if you assume linearity, then that response function can be convolved with any temperature forcing time series to give the ice sheet disintegration or melting response to that subsurface ocean warming. And then finally, that gives you sea level rise. So I've got a bunch of different emulators linked together, and they're all drawing from different data sets. You know, these top ones are drawing from the global climate models. This one's drawing from some standalone ice sheet models, and they're all using different kinds of emulators. One is using a differential equation, one is using a hierarchical linear regression, and one is using an impulse response convolution model. And you can choose that as appropriate to the kind of data you have. So now we're working on adding process fidelity, where we're doing some very high resolution regional simulations of ocean circulation and ice sheet disintegration, 5 kilometers in the ocean, up to 2 kilometers in the land, in ensembles where what we're perturbing is these inputs, which are forcings from the other part of the system. So the subsurface ocean warming around the ice sheet, or the atmospheric forcing onto the ocean from global climate models. And we're doing a multi-model ensemble of these regional models where we're driven by kind of the global atmosphere-ocean boundary conditions to derive these response functions with a much more credible numerical model. And then we plan to stick those things into this chain of emulators and build emulators of these new ensembles. And in principle, you can add more stuff. You can add hurricane models and flood models and all of that stuff. What you have to do is run ensembles where you're perturbing the inputs, where the inputs are something you're getting from one of the other models or data sources. And so this addresses both overconfidence and underconfidence in the multi-model ensemble. So overconfidence, you can sample, here's my blue envelope of multi-model uncertainty. You can sample something outside of it into the tails of this distribution that doesn't exist in the multi-model ensemble. And if you care about risk and what is the worst sea level rise you could get, you might want to sample that. But another thing you can do is you can sample stuff that can never exist in the multimodal ensemble. What's the worst case for sea level rise? It's where you get an extremely fast warming ocean combined with a very sensitive ice sheet that's very sensitive to ocean warming. It melts very easily. But the climate model that has the fastest warming ocean isn't the same one as the one that has the most sensitive ice sheet. So if you just took all those models, you would never see that combination. But here we can mix and match. We can sample that highest warming ocean and the highest ice response at the same time, independent of how they're actually implemented in models. And then the last thing we can do is, now we can try to constrain all of these processes. So if you constrain one of these processes, like the ice response to ocean warming, that should propagate back up this network. So if you say, well, this is the range of allowable ice melting and ocean warming that we see in observations, then we rule out some of that envelope that the models said because they were biased. But in order to get some observable sea level rise, then we might have to adjust things upstream of our model to compensate. So we lowered that response function, but we might have to raise another response function upstream of it to get the same sea level response at the end of the day. So then it's kind of like these deep network type ideas where you're composing emulators and you have to adjust them all throughout the graphical model. This is the last conclusion slide. Actually, that's not the conclusion slide, but I just said all that stuff. So conclusions. Given these numerical models as examples, we want to find a way to sample a wider space of possible model structures, thus converting structural uncertainty into parameter uncertainty. And I'm taking different approaches in different settings. If the setting is, we have a bunch of similar class of models, and we want to combine projections from them, I'm doing the hierarchical Bayesian multimodal combination. If instead we have like a single PDE class model and we want to perturb its dynamics to see what's consistent with observations, we're using the local operator inference and constructing reduced order models. And then finally, if we have this kind of heterogeneous hierarchy of models describing different processes, we have this Bayesian network of input-output response simulators. Thank you.
There was this point with the shallow water equations where you try to learn, say, the operator from the data. Isn't that a very delicate thing? First of all, the shallow water equations is already a reduced model. And it really represents the Navier-Stokes equations, which are just too complex to do. But it is subject to a lot of subtle constraints like positiveness, wet-dry regions, and all these delicacies. So when are you confident that you can learn these things from models, in particular when you prescribe from the beginning a certain vicinity of data, and you may subduing some global effects, and you may be cutting off something from the very beginning, which you can never go back to by these data constraints, or like a CFL condition that may be too, and things like this. So is that? Is that really, can you
So by the way, we're taking this to a more complex model. We've got the 3D ocean primitive equations in a real professional class model. But to make this really practical, you're going to have to do a few things. One is you're going to have to try to write down everything that you think the dynamics should respect. And some things you might not be able to write down, and sometimes you might have to learn them from simulation. So if it goes unstable, then maybe you just rule that out through history matching because you can't write down the full stability criterion in the nonlinear system. But for other things, you can write it down. But the other thing that modelers do is they go through exhaustive sets of test cases, and they say, well, it's got to reproduce this thing where I know the analytic solution. And we basically have to go through that same process and say, in all these very different settings, we will only consider dynamics that fit all of those test cases to within some tolerance.
a quick one. Come back quickly. If you, yes, you carry on. Yes, you. Yes.
And then the POD, so the linear reduced models. I remember hearing Andrew Maida talking about this, where he clearly demonstrated that this was only able to catch 5% of the real dynamics, but rather a nonlinear reduced model actually did much better. Any experience in this regard?
Yeah, so we've tinkered a little bit with nonlinear reduced models, but I think it's going to be very case dependent. And I'm not trying to solve reduced modeling. I'm trying to solve structural uncertainty. So I'm basically assuming for the problem I'm solving, I have a reduced model that somebody worked out, and now I can do my inference and perturbation stuff on top of it.
There's another question. You, I think you.
Yeah. Also on that, the local dynamic operator. So you make the assumption, right, that it's invariant in space that should apply. Is that? Do you also assume that about time?
Yes. But you can sneak some stuff in there. So if you have like, you know, some spatially varying or time varying forcing or something, then you can include that as a covariate. So it depends on the state of the grid cells plus that thing, where if you knew that thing, you could predict how that cell will evolve.
Yeah, hi Nathan, great talk, I really loved it. I was wondering about your first example with the climate sensitivity. Are some of them, if we knew something about how those multi-model ensembles arrived in our databases, would that change some of the analyses that we're doing? For example, if they all tuned the climate sensitivity to try and get it about right, how would we handle that?
Yeah, so, I mean, at some point we're assuming that there's some sneaky dependence between models that we have to account for. And, you know, you could in principle account for it by saying that these are all highly correlated in some way, and you can specify it through that means. You could also just try to overinflate, so you say, well, they're all overconfident, so I'm going to use some heavy-tailed thing to pull them together and allow more probability for something to be outside of what these things say. But yeah, it's something I'm still thinking through.
Michael.
So surely what you actually want for the multi-model is not tuned runs of the model, but an ensemble of runs for each model, better an emulator for the model, and better an emulator plus a structural discrepancy. Now, at the moment it doesn't seem very realistic to get this, but if we had a methodology which said, if only you guys would give me all this, here's what we could give you back, we might start encouraging good practice in sharing. So I think now is the time to build the methods for doing it, to encourage people to do it.
I'm not sure that was a question more of a sales.
Well, you might tell me you have a methodology for combining them.
Oh yes, sorry. That wasn't sorry, Michael. I didn't mean.
No. But it's something I'm thinking about, yeah.
I'm going to, can I ask you, please?
Okay.
I'll go on.
About this global warming and this magenta curve. So how come you have that the actual state is below or almost on the bottom of all these 19 predictions? And how you can estimate the future from this, because it's practically an outlier.
So it's not really an outlier. If you look at what the observations do to the model estimate, it brings the green curve down to the magenta curve. So that's a shift of, you know, it's not trivial, but it's about like, you know, 25%, 30% shift. So the real thing that, you know, I think the models are useful for is if you were to do this purely observationally, I mean, look at the prior. The prior goes way out because, well, there's a long list of reasons why we can't rule out high sensitivities a priori. So the main thing the models are doing is cutting off some of the high end of those climate sensitivities. And then the residual bias in there is something we're dealing with observationally.
I have a quick question, and perhaps I'll do the last. Just quick. So what I find very interesting is that you've got diagram, you've got causal arrows. So you've got a type of causal, sort of computer-based cause, so somebody can go and intervene, and get a causal chain. But to what extent are these causal relationships actually real in reality, as opposed to artifact of somebody playing with the computer code? I mean, there's a distinction there.
Yeah, I mean, I think there are a lot of actual causal relationships, and then one advantage of models is that we have some hope of actually teasing them apart. If you try to do it purely in a data-driven causal identification way, it would be hopeless. But in a model, you really can, perturb the surface temperature and see what the ocean will do in response, and see the patterns of kind of like waves are carrying energy from here to here, and you actually, those of course may differ across models, and then that gets us back to structural uncertainty. Maybe none of the models are doing that exactly right. But I think the models are actually, this is one of the main ways that we should be using models and are not, by doing these sort of intervention experiments with them.
Fantastic. Anybody dying to ask a question? Okay, well, thank you very much indeed, and all the other speakers.